Today we're going to start talking about the robotics project, the final project, and we'll get into it just little by little. But we'll go through some electricity stuff first, and then I'm going to say a little thing about the robotics project, and then I'm going to show some videos and just talk about what we're trying to get done. So, okay, let's start by just talking about electricity. So I want to go through this homework first, and then we'll go through like a little refresher in person. So for number 2, here's our circuit. And so calculate the voltage and current, and then, well, I'll do that first, I guess. Okay, so how do you calculate the voltage and current for this? So we know that if we lump these two together, like think about wrapping these two resistors all up in tape and calling it a single resistor. Then we can think of this as a simple circuit like this, where that resistor is the sum of those two resistances. So that's 10,000 ohms and 1,000 ohms. That's 11,000 ohms. And the voltage is 6 volts. And so we know that the voltage across here is 6 volts. And now we want to figure out the current. And so I'm going to use Ohm's law. And we have that 6 is equal to 11,000 I. And so that current is 6 divided by 11,000. Or 0.545 milliamps, or 5.45 times 10 to the minus 4 amps. Okay, so that's the current that's going through those resistors. And now we can separate those out. So we know that there's 5.45 times 10 to the minus 4 amps going through that one. And because they're in series, there's 5.45 times 10 to the minus 4 amps going through that one. And now we can use Ohm's law to find the voltages on those two. The one on the left is 10,000. So Ohm's law says the voltage across the 10,000 is equal to 10,000 times 5.45 times 10 to the minus 4. And so that voltage is 5.45 volts. And then you can use Ohm's law again, or you can just subtract from the total of 6 volts. But if we use Ohm's law again, it says that the voltage across the 1 ohm resistor is 1,000 times that same current. And that is 0.55 volts. You know, there's a little round off error in there. I mean, I rounded off a lot, but they do have to add up to a total of 6 volts. Anybody have any questions about that one? Okay. So now we're going to get into the multimeter stuff. And now it says, okay, draw the wires and the dial position to measure the voltage across the 1,000. Okay, so what do we see here? This terminal of this resistor and this terminal of this resistor are on the same row. So those two are connected. Okay. And then this terminal, it's a little hard to see, but it's connected there, and this one's connected there. So we can connect the battery. We can take the positive and connect to this one, anywhere in this row, and that makes that positive current flow into this side of the resistor. And then, since these two are on the same row, the electricity, after going through that resistor, is going to go through this resistor. And now we can take a wire, put it in anywhere in this row, and connect it to the negative terminal of that battery. Please feel free to stop me anytime, and I'd be happy to go into more detail about this. There's no doubt that this is confusing to everybody when you first start seeing electricity. But so I'm going to take, let's say, a red wire. The colors of the wires don't change anything. It's just for organization. But so I'll take a red wire and connect it to that. I think the 10,000, well, it doesn't really matter the order, but the 10,000's on the bottom, you're right. So really, if I want to match that circuit exactly, I would go like this. And then, so it's going to flow through the 10,000, wait. Yeah, so it would flow from the positive through the 10,000, then through the 1,000, and then the 1,000 would connect to the ground. I could have used a better colored background here. Okay? Are you with me on that? And so now so if you wire it up like that, then current is flowing through that, circuit. Now, if we want to measure the voltage across the 1,000 ohm resistor, remember, to measure voltage, we keep the circuit intact and we just let the multimeter observe what's going on. So I'm going to take my red wire and I'm going to connect that. So I want to put it on the two sides of the 1,000 ohm resistor while the current is flowing through here. So I'll connect that over here. And actually, if I want it to be if I wanted to read a positive number, I guess I need to connect it on this side. And then I'll take my negative terminal and connect it here. Okay. Anybody have any questions about that? It gets a little messy looking as you go, but all I did was I have the current I have current flowing fully through the circuit, and then I connect my positive voltage lead to the positive battery side of that resistor. My ground, I connect to the negative voltage side of the resistor. And then the dial, well, this 1,000 ohm resistor is going to have 0.55 volts. I want to put the dial to the lowest voltage that's higher than that voltage I expect. So that's going to be over here. Yep.
So it's keep the positive value because the positive current direction is the same way, right?
Yeah, it's the same as the current direction. Yep. So if you know the direction of the current, if you think of the current going into an element, you want your positive lead of your voltage to go on the side the current goes into. Okay, but it really doesn't matter, practically speaking. If you had done the positive instead to the negative voltage side, if you had switched which one of these go to which side of that resistor, you'd get the same answer. It would just have a negative sign there, so it doesn't really matter. But it will tell you, I mean, if you want to use it to make sure you're thinking right about the polarity, it will tell you whether you're thinking right about it. Any other questions about that? Yeah.
So even if you started from the 1,000 hertz to the 1,000, like 1,000 with like wire,
yeah,
it's still okay.
Okay, so yeah, I mean, so if I instead wired it up like the positive going to the 1,000 first and then the 10,000, nothing we're doing here is going to change. But what I was just saying now is leave the circuit the way it is, but if you just change the order of the leads coming from the multimeter that's observing it, all you'll get is a negative sign on your readout. But yeah, nothing would change about the behavior of this circuit if the positive first went through the 1,000 and then went through the 10,000. And I mean, you can see that if you look at the way those calculations are done. Nothing would change about the calculations, Any other questions about that right now? I'm going to do number 3 also when I'm done with this. So that's B. Now C. Now we want to measure the current through the 1,000 ohm resistor. Okay, so this time, remember, if there's one thing you remember, I want you to remember about the multimeters, it's that when you measure current, the current, you're not just letting the multimeter observe a circuit that's already going. You have to break the circuit and force the multimeter to become part of the circuit, okay? So this time what we're going to do, yeah, that's right. So so this time, let's see, so we'll have, So let's say the positive goes to something that's not yet connected to those resistors, okay? Then we're going to go from, okay, and we have to think, I guess, a little bit about roughly how much current we expect to be going through this 1,000 ohm resistor. That's why we did the calculation to start with. It's a very small amount. So we can use the milliamps thing. It was only like half a milliamp or something like that. So I'm going to go from here to the milliamps. And then the ground is going to go to the 1,000 ohm resistor. Now, so the current is going to go from the positive through the multimeter. Then once it comes out the multimeter, it's going to go through the two resistors, and then finally it's going to go from this resistor to the negative terminal of the battery. So do you see how this is different than the way we set it up to measure the voltage? Instead of having so when you're measuring the voltage, the current is running whether the multimeter is measuring it or not. When you're measuring the current only runs once you plug in the multimeter. Okay. And as far as a measurement, well, I said from our calculation, we expected half of an amp about. And so we want the smallest measure that's bigger than the current we expect. That's 20 milliamps. I did this whole calculation and got a current of 0.545 milliamps. If you did this, if you wired this stuff up to a battery in there and a resistor in there, would your measurements give you close to these exact values? Well, they would if your battery happened to be exactly 9 volts and your resistor happened to be exactly 1,000. But remember, those are going to be off. So if you need really precise values, then you need to measure those before you start. Yes?
Just going off of the answer for this question, do you want us to have the battery be a 9 volt like in the picture or a 6 volt like in the question we did the calculation?
Oh, good question. So pretend that's a 6 volt battery, I guess, in the picture. For the calculations you're talking about, though, right?
Yes, for the calculation.
Yeah. Yeah. Yeah, pretend that's a 6 volt battery. But if you've already done it and did it the other way, that's fine with me. I mean, all I'm trying to do is help you get used to wiring up these multimeters and these circuits. Any other questions about this? Okay. So that was B. No, that was C. So now D, so now measure the voltage across the 10,000 ohm resistor. So the 10,000 was the bottom one. again, since this is voltage, we want the circuit to run without whether the multimeter is there or not. So I'm going to go positive to the 10,000. Then it'll go through the 1,000 and then to the negative terminal of the battery. So that circuit is closed now. Current is flowing. And now to measure the voltage across the lower resistor, the 10,000 ohm resistor, I'm going to take the positive. That's not the positive. I'm going to take the positive voltage and go to one side of the resistor. And then I'm going to take the ground of the multimeter and go to the negative side of that resistor. And then for the 10,000 ohm resistor, we expect a voltage of about 5.5 volts. So the smallest voltage that's still bigger than that is 20 volts. So I'll put the dial there. Okay. And then, let's see. Well, I'm going to skip these two because these are measuring the current through the 10,000 ohm resistor and the current through the battery. All of these elements are in series, and so all of these currents are going to measure exactly the same. And so, well, does anyone have any, would anyone like me to do one or both of those? It really, in a way, it's kind of, so the way you measure the current is to put the multimeter in series with what you want to measure. Well, everything here is in series, so anywhere you break this circuit to put the multimeter in is measuring the current through each one of those at the same time. Okay, that's why it's sort of a funny question that some idiot asked you. Okay, well, let's go on to number 3. Okay, so this time those two are in parallel. And you know these are in parallel because, like, if you think of the definition of parallel, the electricity comes from the positive, gets to here, and now it has a choice to make. It can either go through the 10,000 or the 1,000. And then whichever way it goes, it'll meet up here. Okay, so this is parallel. And the first thing we're going to do is calculate the voltage and current for each of these. Well, we know that for parallel resistors, the voltages are the same. So it's 6 volts across each resistor. So I'll draw what we know so far. We know that, so here's the positive, negative. since the positive is over here and it's connected by wires to this side and this side, we know that the positive of the voltage is here and here. So the negative has to be here, and this is 6 volts, 6 volts. Okay. And now we can calculate the currents. We know the currents are always going to go from the positive to the negative of those resistors. So they're going to go that way. We'll use Ohm's law to calculate it. We have the 10,000 above. So 6 volts is equal to 10,000 times the current through the 10,000 ohm resistor. And so that I10 is 6 times 10 to the minus 4 amps, or 0.6 milliamps. And then for the 1,000 ohm resistor, 6 is equal to 1,000 times the current through the 1,000 ohm resistor. So that current is 6 times 10 to the minus third amps, or 6.0 milliamps. So I can write that up here as, so this is 0.6, nope, that's the wrong place. So the one on the bottom is 6 milliamps, and the one on the top is 0.6 milliamps. Anybody have any questions about that one? We're not, for us, like parallel resistors are not going to be super useful. Really, series resistors will be useful sometimes, maybe, because if you don't have a big enough resistor, you can put resistors in parallel and they just add up the resistance values. So if you want the equivalent of a 1,000 ohm resistor, but all you have is 2 500s, you can just put them in series and it does the same thing. This one won't be as useful for us, but it's helpful for understanding how this stuff works. And then the current for the battery is just the sum of these two. So this is 6.6 milliamps, or 6.6 times 10 to the minus third amps. Okay, so in this picture, the 1000 is on the left, and we want to measure the voltage across the 1000 ohm resistor. So we want to measure the voltage across the one on the left. These are in parallel, so the voltages are the same across both of them. When you're measuring voltage, remember that the current is flowing. You close the circuit and get the current flowing, and then you put the multimeter on a current that's already flowing. So first I'll connect the circuit. The positive goes through. Now, since this row that I have this connected to includes one side of each of those two resistors, the current comes through the positive and has a choice of whether to go through the 1000 or the 10,000. So this is going to be going in parallel. Yeah.
When I was working on this, it looked like the left one was terminating out. Overall.
Oh, it does look like it, but that's just how it's bent. Well, it looks like I drew it wrong. I think they're both connected here. You'll just have to take my word for it.
Then how do we do 3E?
Okay, I'll get to that in a second. Okay, so that current is going now. Current is being drawn out of the battery, going through those two parallel resistors. If you want to measure the voltage now, I'll take the positive and connect it on this side, the ground, and connect it on this side. The current is 6 volts, and the voltage is 6 volts. So the smallest voltage that's bigger than 6 volts is 20. So I'll put the dial here. So now the current. Which was the one you were asking about?
Yeah, well, it's a 3CE and F about.
Okay. Okay. So now we're going to measure the current, and that means we have to break the circuit, and the circuit can only flow once we have the multimeter attached. And we want to measure the current through the 1000 ohm resistor. Okay, so the positive of the battery, I am going to go to a new row. And then I'm going to go from, okay, so we're doing this for the 1000 ohm resistor. What did we get for the current through the 1000? 6 milliamps. So I can use the milliamps measurement of the multimeter. And the positive side is going to connect here. And, this is not possible the way I did it, is it?
I think it is possible if you assume that the resistors can terminate
On different, right, well, that's not how I did it. So yes, so the way I did this, it's not possible. So let's say that I was smarter and I did have this go one row above this one. Okay. So my positive terminal of the battery, I will go here. And then from the negative terminal of this 1000 ohm resistor, that's where I'm going to put the 1000 in. Let me draw that different. And then the ground, I'll connect to a different one. Let's say there. This is getting so messy. Okay, so now it's going to flow through both of these two resistors, but when it goes through the 1000, the electricity that chooses the 1000 is going to, after it gets through the 1000, that electricity is going to go through the milliamps, out the ground, and then, oh God, these are going to have to cross. So then from the common, we can go to here. We can also join this to here. And now those are connected to the same one. And so this is a hideous picture. But now it can go through the negative. Okay, so let me draw this in a better way to do this. Yikes. So a better way. So let's say that we have the breadboard. And let's say that the 1000 goes like this. Let me make that one longer, actually. So let's say the 1000 goes like this. And the 10,000 goes like this. And here's the battery. I'll make this the positive and this the negative. And then over here, we have the milliamps and the common. Make a few more rows. Okay, so the positive of the battery is going to go to here. And from there, it's going to go two places. It's going to go directly to this, and it's also going to go through the multimeter. When it comes out of the ground of the multimeter, it's going to go through the 1000. And then when it comes out of both of these, it's going to go to the negative. Still had to cross it once, but that's a little clearer what it's doing. Well, you're welcome to skip those parallel questions on the homework, because the way I took the pictures really kind of made it impossible. But I mean, what we're just trying to get to is an understanding of how this works. So just try to understand what's going on there. And like I said, the series resistors are going to be more useful to us in this class than the parallel resistors. So I guess that's a positive, but try to understand what's going on there. Anybody have any questions about this picture here? Okay. Any other questions about that homework assignment? Okay, before we get into, well, I think that's enough electricity stuff. Let's just get into talking about the Arduino project. So now we're going to start talking about the Arduino project. Robotics project. And these kits have, Arduino is the company that makes these. And it's a little board that looks like this. Let me show you one of them. So it's about this big. And this just has some protective stuff on the bottom, so it's a little thinner than you see here. But there is a little microprocessor here. And then there are two lines of pins on the two sides. There and there. And we'll talk in detail about what some of these are. There is a ground over here. And a ground over here. And mostly what's going to matter to us are these pins on this side. These are the digital pins. Okay, so these digital pins, I'm sure you've heard people say that digital stuff is all about ones and zeros. And those ones and zeros are really defined by a voltage between each of these pins and the ground. So if you measure the voltage between a digital pin and the ground, it's either 5 volts or 0 volts. Okay, 5 volts is the 1, and 0 volts is the 0. Okay, so these voltages that you could get, you know, once you're going, if you connected a multimeter ground to this and a multimeter voltage probe to one of these pins, you would measure either a 0 or a 5 volts that way, okay? And by adjusting the voltage of the pin compared to the ground, you can transmit, you know, information. Now you can use these pins to read inputs. So examples of inputs are what's called a ping sensor. That's a ultrasonic rangefinder. Accelerometers. Touch sensors. Optical sensors. And the idea with all of these is you plug them into these pins, and based on what they detect, they send a certain voltage to the pin. Okay, so that's if you're using them as inputs, or you can also use them as outputs. And examples of those outputs would be lights, speakers, motors, and those are really probably the 3 most important. And so a robotics project is really just, and these communicate with each other. Through a program that you load onto that microprocessor. Okay, so you could write, for example, you could write a program that says, check an optical sensor for a human. Okay, and then once a human is detected on the optical sensor, the next part of your program says kill all humans. We're not going to do that in this class, but you can make a lot of money for programs like that. But the the idea is that you write a program that determines the relationship between what you detect using the sensors and what you do using the outputs. Okay, and this could be, you know, maybe a more reasonable thing would be like a pretty common project is, you know, you can make a car that travels along a line on the floor or something. Well, you have optical sensors that are trying to keep a line in between the two wheels, you know? And when the optical sensor detects a change in the darkness that it sees, it's leaving the line. And so based on that, it says, okay, increase the speed of the motor on the left or increase the speed of the motor on the right to recenter the line, that kind of thing. Okay, and we'll have plenty of time to talk about what the syntax is that you use to program this stuff. But for now, that's just kind of the basic idea. You're always reading you're not always optical sensors, but you're always reading input values. And then your program based on the input values is saying what power to provide to do something, okay? There's one problem. And that is that the current that these digital pins can provide is tiny. So they can only provide about 20 milliamps of current. That's not nearly enough to power any kind of motor or anything like that, you know. You can, some LEDs can use that amount, so you could light some things up, but there's very little useful that you could do with that small an amount of current. So that's not enough current for most motors. So how do you use this program to say you wanted to power, say that you wanted to turn on a car engine or something? Like how would you use the information from the inputs to generate a big current? And the answer is transistors. And in this class, unless you're doing something special, you're really only going to use transistors as switches. So we'll use transistors as switches. And the idea is the small current from the pin is enough to switch the transistor. Then the transistor can handle those bigger currents. In some cases, if you want an even bigger current than the transistor can supply, you can use the transistor to switch on something that can allow even more current, like a mechanical relay. Okay. So then the transistor can handle more current. The transistors that are in these robotics kits are BJT transistors. They can handle currents of maybe up to 1 amp. An amp is quite a bit of current, but not always enough to power a big motor, you know, depending on what your power needs are. If you remember the little talk about transistors, MOSFET transistors can handle bigger currents. So we don't have MOSFETs in your kit, but we do have MOSFETs over here that can handle bigger ones. So depending on your needs, you know, we have stuff that you can use. And then if you need more current than that even, we have mechanical relays. I think there are mechanical relays in the kit. So the idea is you can use a transistor. So you can use the pins of your board to switch a transistor. Then you can use that transistor to switch a mechanical relay. And then that's enough current for just about anything. I mean, we've used really big motors before, like windshield wiper motors and stuff, and that's enough for that kind of current. Okay. So the last thing I want to say is, so the robotics project, let's talk about what this is. So these are group projects. And you're almost certainly going to have to communicate on this stuff outside of class, although a lot of it you can sort of delegate and coordinate who's going to do what parts and stuff like that. Unless you have objections to it, I mean, usually it's just the people sitting at a table or a group. Anything between 2 and 4 people is fine, and I think that's what we have at the tables. But if you want to combine tables or if you want to mix it up, that's fine. I really want to focus this semester on robotics projects that are simple, but really focus on being well done. I'm going to show you some videos of like some other projects you can do. I have a little bit of footage of like an old, of some old projects that people did like 15 years ago or something. But I just really, and they've been kind of like taped together, you know, like wobbly or whatever. I'd really like to focus on simple ideas. Don't try to promise too much, but make sure it's well done. Everything works smoothly. It works consistently. We have the Fab Lab available if you need laser cutters or 3D printers. We'll get your stuff 3D printed here soon too. And then sort of related to that, I want to focus on how your implementation of these things reflect the Dieter Ram's 10 principles of design. Okay, so I want to keep thinking about how you can improve your product, your project, by thinking about these principles. Okay, so let me just show, I just have a few videos I want to show you, and then you'll have time to chat with each other, look online, think about ideas. I can answer questions, but it's just, you'll have a little just kind of brainstorming time today. Okay, so was this the one? Well, let me first show you, this footage that I just happen to have from 2009. So there was a lot of Legos used in these days, but this is one. This is a card shuffler. So there's an optical sensor down here somewhere that. So I think this thing, to start it, this thing flips up, moves all the cards over here. Then an optical sensor is looking to see whether there's daylight while this thing spins and shoots these cards in here. And so it shoots all the cards in there. Then eventually all the cards are moved back over to the right side, and this optical sensor sees daylight, and this tips back up to shuffle again. Okay. So you can sort of see the interplay between the input and the output. That's my voice. That's what I sounded like 15 years ago. That's our old dean. That's a boy genius. Not really. So it's just an optical sensor that detects when something comes up to the drawbridge, and then it opens, I don't remember if this thing. That thing tried to, I missed it. So this thing, scanned around until it saw its target and then moves towards the target. And when it loses it, it scans around again, adjusts its position, and then moves towards it. These are all kind of simple ideas, but this one. Oh my God, I can't believe no one died from this one. This they brought in this giant refrigerator and cut this hole in it and kept cans of pop inside the refrigerator, and I don't remember how maybe there was just a button or whatever, but it just launched Coke cans at people. Okay, so sort of gives you an idea of what kind of stuff you're doing. We have the Fab Lab here now. We have the ability to make very precise parts for the robots. And so, like I said, I would like to focus on designs that are simple. Do a simple thing, but give yourself time to make improvements. Think about how to satisfy those design principles. Okay. Anybody have any questions right now? So let me show you one video. Let's see. I don't remember which one of these. Let's see what this one is. We don't have every kind of sensor, but we have a lot and we can get more. So give it up with the parking stuff. Okay, so